Hi, kitty cats. Western society prides itself on being scientific, but most of the science that's promoted today is actually political opinion, weaponized only by statistics. So, what's the difference between science and statistics? And why is political opinion not the same as science? And finally, what would a scientist, say me, consider normal? Well, let's talk about science, statistics, and gender. Well, let me first of all see. Here we go. Look at I got somebody called Keeping On says it's a good topic. I'd love to. So Keeping On says they only took Statistics 101. I'm actually going to talk about an application of statistics. So it'll be hopefully this will end up really turning your crank. I don't know where I want to go. It'll keep you keeping on. But first, let me do the opening stuff. I am Dr. Amethysta Herrick. I am an author and a podcaster. I discuss identity and gender from a scientific standpoint. If you look below, you can check that link for more information about me and the work that I do. My website, obviously, purplepotclan.com there. You can follow me on all the social media networks that I'm on, as well as view the articles that I write and all the podcasts and various things that I do. So if you like this content, you might consider subscribing at purplepotclan.com. You forget about you might. I'm sure you will. You can get a subscription for as low as $5 a month. And I also publish articles and podcasts by other contributors. So if you're interested in having your work published, having your work published on the Purple Pot website about identity and gender, by all means, please, or at least just by this mean, email me through the contact page on that website below. So here we go. All right. Let's see. I also see Margie. Hi, Margie. It's good to see you. It's been a little bit of a while here. She says, good morning from Kiwiland. And then we got Miss Chief. Hi. Baby Amethysta, baby, where'd you get those eyes? It's interesting. My father had very similar eyes, which bugged me a little bit, for what it's worth, because he and I didn't get along particularly well. But we're going to run with it. All right. I want to talk about how statistical opinions, and I want to call it statistical opinions, how they play into Western society. I got a comment from a friend of mine recently. I was talking with a friend, and she made the point, or she said, well, what is normal anyway? It's 2 sigma, right? And this is a reference to statistics. Keeping On is going, oh yeah, sigma, sure, there you go. It's a reference to statistics. There's the lowercase sigma in this case. Lowercase sigma is used to denote what's called a standard deviation. And this is a concept in statistics. It's not the same as uppercase sigma. Uppercase sigma is used for summation. So you're adding a set of numbers. Lowercase sigma has to do with a standard deviation in a set of numbers. Unfortunately, when it comes down to calculating, to computing lowercase sigma, it actually depends on uppercase sigma. So thank you very much, mathematicians. I don't know what's going on there. But speaking of mathematicians, I related this to a friend of mine who has a master's degree in math. And you can imagine we have exceptionally interesting conversations. I said, yeah, I had a friend who said, what is normal? It's 2 sigma. My friend immediately went, no. And it made me realize that Western society at this point has a tendency to conflate a statistic with science. Now, I'm going to tell you there's an obvious relationship between the two. Science depends a lot on statistics, and I'm going to make that correlation at some point in this discussion. But both of those are different processes. And both of them have very different goals. Now, I don't usually talk about this. I don't remember the last time it came up. And I also don't talk about my past employment history frequently either, for what it's worth. But in my past employment history, I have been a professor at 2 major universities here in the United States, a professor of chemistry. And when I say major, it's like 30 to 50,000 students, I would guess. So I was a professor at a university in California, professor at a university in Colorado. Altogether, I would say I have about a total of 7 years, 8 years, somewhere in that general area, in academia. And that's including, to a certain extent, my graduate work at a university in Georgia. So I am an analytical chemist by education. And so my education, much of the curriculum revolved around experimental design, which sounds super fascinating, right? You go, oh, experimental design. What I tended to teach was something called error analysis. And this is the application of statistics I was going to say for keeping on here. Error analysis is a very important process. It's really the way that we understand if good science has been performed. I think that's the way I want to put it. Now, in this discussion, I don't want to get too technical on things because I understand getting too technical is just going to be boring. Like, I understand that well enough, right? But what I want to talk about is, first of all, what is the foundation of science? You know, when we look at science, what are we looking at? Is it statistics? So let's talk about the foundation of science, but then I also want to talk about when you have used statistics, how those statistics can be manipulated. And this is used to create opinions that sometimes the data may not even support. And then once I've gone that far, we can have sort of a fun bit where I'll talk about a few practical examples to show why and how. So I'll give you a few questions to ask, but show why and how we should always question the statistics that you have some politician or, hey, even your friend maybe throwing out there. There's Louise. Hi, Louise. Good to see you. All right, let's talk about the foundation of science. At base, science is concerned with data. And you go, okay, sure, there you go. In particular, what we're talking about is acquiring data and then interpreting data. But you're talking about a set of data. Usually that means more than one observation. So a set of data. These observations are made of the natural world. And it doesn't have to be anything in particular. It doesn't have to be chemistry. It doesn't have to be physics. It could be the number of cars that drive past a particular point on the freeway. It could be the colors that you observe on seashells in some tropical bay where you're staying. Maybe Margie does, I don't know. Or if you're like I am in graduate school, it could be observations on the crystal structure of compound semiconductors electrodeposited on annealed noble metal surfaces. Right? And see, now I wonder why I don't have any friends. I think that was why. Just right there. But all of these observations produce a set of data. And presumably they hold value. Presumably they hold value at least to the person making the observations. Because if not, I guess I'd question why you're making the observations. But you end up with a set of data. Now, typically when we're doing science, when we're talking about science, it's not something that's done blindly. When you're starting out, like when you're an undergraduate doing general chemistry or general physics, general biology type laboratory classes, sometimes you do get some of these, where you're doing some science and you kind of go, why are we doing this, right? And then you go, oh, okay, that was to reinforce some principle that we learned. But almost never do you just have like a solution of yellow and like a solution of blue and you mix them together and you go, hey, look, I got green. Right? Because yellow and blue make green. Every Gen Xer out there who's used a baggie is aware of this. But usually you base science on previous knowledge. Like what was in the yellow solution? What was in the blue solution? What in the green solution? Was there a chemical reaction? Are these colloids? What caused all this to happen? What are we looking at here? If we go back to some of the others, why do we care about the freeway? Maybe we're trying to study traffic patterns or accident patterns. Maybe we're concerned about the effect of the environment on the color of seashells in these tropical bays. There was really not a lot of use for the compound semiconductor crystal structure. I think I'm just going to admit that right here. I'm going to leave that out. So, but usually what we do is we start from past knowledge, gleaned from observation, and then we try to add to that knowledge. So when we're doing science, and I have a friend who has a shirt that says, stand back, I'm doing science. Usually when we do science, we're talking about two processes, in particular two processes, and that's acquiring a set of data and then interpreting said set of data. Acquiring a set of data is what I did a lot of, I do a lot of thought on this. Usually we're talking about designing an experiment, designing experiments to set up observations. So how do we get to a point where we can even test something to make observations, where we can actually make these observations? Sometimes you end up having to develop a method, like an actual way to measure something, to observe the phenomenon at all. So, for instance, in my work as a graduate student, I developed a technique called cathodoluminescent surface sensitive spectrometry, which sounds really impressive. It did to me at the time. And then sometimes this also includes building instrumentation to perform these measurements. So cathodoluminescence means you have to shoot an array of electrons at something, and if you're going to do that, you have to have a relatively high vacuum. So I had to develop instrumentation to deposit something on a physical surface and then get it into an ultra-high vacuum to do some sort of analysis. That's just acquiring the set of data, and so that's a significant amount of science. But the other part is interpreting that, because I ended up taking a total of about 2 weeks worth of good data before I wrote a doctoral dissertation. But you want to check the context of that data. For interpreting this, was this data acquired cleanly? Like, do we know that we got data that is reproducible? That's really what that is. But there are more subtle questions to ask. Was it the right data to acquire? Like, if you designed experiments, do the experiments that you're running actually measure the data that you expected to measure? Because sometimes it doesn't. And then maybe more importantly, does the data that you measure even fit the hypothesis that you're trying to test? That also, part of the interpretation is determining the meaning of the data. So this is checking the context. We haven't even looked at the data at this point. Now you're determining the meaning of the data. Are there trends that we can observe? Does the data that we acquired, does it fit our existing hypotheses? And if it doesn't, do we need to change our existing hypotheses? And if you look at much of the debate, and here I'm actually going to use debate without quotation fingers, much of the debate around science falls into those categories. We debate, techniques. Is this technique to acquire a set of data, is that a good one? Is it a bad one? We tend to debate whether the context of the data makes sense. How does it fit into the rest of the universe? And this is really where peer review comes in, because I'm going to tell you, the scientific community stands ready to step in and criticize whatever you got. They're ready to go. You got some data, they'll come in and criticize it. Live it up. But usually a set of data is, frequently, let me say frequently, a set of data is insufficient to draw much in the way of conclusions. And so then we turn to something else. Usually we turn to statistical methods. So let me check comments, because there's got to be. So far, this is already a lot of fun, right? All right. So Margie says there are a lot of errors to analyze in general social views of identity. It's a really good point. I'm going to get to something similar to that, so hold tight on that. I love Louise's comment. 9 out of 10 statistics are made up. Yep. Isn't that funny? Mischief asks, what metal surfaces did I do? In particular, I used a polycrystal, a crystal of gold that was polished to 3 crystal faces, 100, 110, and 111. So one's a hexagonal, one is kind of a rectangle, and one is a square surface, and that's why we polished it to those particular crystal faces. But I used that gold crystal. I also used stainless steel when I was doing some other stuff that was polycrystal, and that didn't make a difference. That was it was really just a surface to hold some other stuff. But I've also used copper, magnesium. We had a platinum crystal in our lab. I think that's about it. Then Margie says, when I talk about ion deposition on annealed semiconductor surfaces, I get butterflies in my tummy. So is electrodeposition of compound semiconductors. Yeah, it was on annealed metals, unfortunately. But it is, guess you're a neurospicy nerd too. Wait, you're trying to say that I am? Hey, Miss Chief says zipped ziptometry. I think that was it was the Ziploc bags. Wasn't that baggies? What was that Ziploc? I don't know. But I got a big quick kick out of that. I remember when one of the very first experiments I did, like, in high school, it was literally take yellow and blue and make green. And I was like, why well, I just saw a commercial along this line? This was not a revelation here. Why are we doing this? There you go. Keeping on says, think they'll stick with cooking. I don't disagree. Okay, so keeping on then makes the point, don't forget cleaning the data from missing or incorrect data where the source is unbiased. Yeah, we're going to get there. That's my next section here. It's going to be great. Ms. Chief says she's only got 10. There we go. Oh, Lizzie, the bird's biting your toes. I'm sorry. That's never good. All right, let's talk about ultimately error analysis. I actually have pulled out my book. I'm having trouble picking it up. I pulled out my book. This is Error Analysis by John Taylor. This book was published in a long time ago, like maybe the 1980s or something. I probably don't need to find. Oh, here we go, 1982. So it was published in 1982. It's a 40-year-old edition. There's no third edition. All right, because error analysis, when it comes down to, is a set of mathematical techniques and sort of a set of logic. You can see it's not even a huge book, right? It's not even a really big book. 300 pages, if we're lucky. Yeah, with an index, 300 pages. But error analysis is important. So this is an analytical tool. But before I talk, I know you don't, I'm sure nobody cares for me to quote some formulas from this, right? So let's talk about something practical. Oh, I meant to bring some dice and I totally forgot. Oh well. Imagine if we have one die, right? So like a regular six-sided die, right? D6. Every D&D nerd out there is going, really? D6? That's so boring. Anyway, standard six-sided die. Labeled 1 through 6 on the faces. If you take this die and you roll it 100 times, you will come up with a set of numbers. And that set of numbers presumably will be between 1 and 6. And on its own, you just go, cool, I got a set of data. So maybe you would try something interesting and say, well, how many times did each number come up? And so you can build what's called a histogram. This is a type of graph that shows the frequency of each number as it came up. Now, assuming you have a die that is balanced properly, supposedly those are going to come out about equal. And that's not super interesting. But imagine if you roll 3 dice. Now you've got 3 six-sided dice. Now you got 3 six-sided dice and you're going to roll those all at once. Okay, so you're going to roll those 100 times again. And now you get a distribution that's dramatically different. Instead of going from 1 to 6, there are 3 1s. So it's going to be 3 and then 3 6s and to 18. You have a data set from 3 to 18. But the way that you're going to end up plotting this, if you plot it, if you got that time on your hands, is going to be very different. Because many of those numbers come from combinations. So like the number 9 could come from a 3 on each of them. Or it could come from a 1, a 2, and a 6. Or a 5 and a 2 and a 2. Or, I don't know, keep me going. But you could also look at permutations. So if you gave those dice labels, A, B, and C, let's say, then maybe you have A is a 6, and then B is a 1, and then C is a 2. But then you can mix those all up because maybe C is the 6. And, so permutations and combinations, you end up with what is a very much more interesting set of data, although not still one of the most amazingly interesting sets of data. And if you really want to go all out, you'll roll 3 different dice, right? So like a D4, a D8, and a D20 or something, right? So you have a distribution that could run from a range of values that could run from 3 to 32, but different dice make different combinations more probable. And that's sort of when you see that, especially graphed out, you go, wow, that's fascinating. Who would have thought that would happen? When I'm talking about the values here, we're talking about trends in the data. And when you try to determine trends from a set of data, that's the field of statistics. Now, statistics is a branch of mathematics, but mathematics is the study of numbers, usually operations among numbers. Statistics describes bulk properties of the entire set of numbers. So, for instance, if you have a set of numbers, or you should say values here, not necessarily numbers, I should say values. So maybe you'll see, if it's numerical, maybe you could do an average of all the values. Maybe you can find the value that occurred most frequently, which they're not always, almost frequently not the same. Maybe you'll look at the relative frequency of the appearance of these values. It's important to note here, statistics are not observations, okay? These are interpretations on top of a set of observations, and often they're mathematical interpretations on top of a set of observations. On their own, these interpretations hold no value. Like, who cares if the average is 8? But the interpretations then can be used to develop hypotheses. And these hypotheses would presumably try to help us explain why these errors or these values were observed. And so there's sort of the fun bit. Let me check out comments really quickly. Keeping on, I swear, I'm just about to get there. All right, let me see. A mischief says 1897. Fortunately, there's actually a picture. This train wreck here, I don't know if that's obvious. That train wreck there is from something pretty early on. I mean, it's a photograph, right? So it's got to be after the turn of the 20th century. But it's that was obviously a big error, right? There was a big error. Lizzie says she failed statistics 3 times. Fortunately, we're not going to talk about statistics, right? There's Brenda. Hi, Brenda. Better late than never. Oh, come on. What was it? 2 minutes? Who cares? So let's see. Mischief says, one of my lifetime embarrassing moments was walking into a store where they had packets of 6-sided dice on display to ask how much 6-sided dice. So the assistant says, what other kind are there? Right. So what other kind of dice other than 6-sided? D&D nerds, right? See, that's the thing. Since 1970, 76, 77, when D&D came out, and we're like, oh, a tetrahedron. That's a die, isn't it? 20-sided die? All right. So I mentioned statistics. These don't add any value, at least initially. We could use those statistics to try to add value, to make hypotheses on why we observe these things. But if we want to determine the quality of the data, which directly affects the quality of the hypotheses we make, then we use error analysis. And that's why I keep holding up my book there. John Taylor, of course, John R. Taylor, paid very handsomely for this product placement, no doubt. I don't even know where he's from. It's like University of Massachusetts or something. But anyway, error analysis is a practical application of these statistics. So it's using statistical methods, most of them. There are some statistics can get pretty ridiculous where you end up going, okay, well, I'm going to go 3 levels deep on, whether or not this data seems, what trends we observe in these data. So error analysis will use statistical methods, but we use those statistical methods to evaluate the quality of the data acquisition. And then, like I said, directly the hypotheses that we're going to draw from the set of data. So let's go back to looking at these 3 dice. Right, we have 3 6-sided dice. We know the values should only be from 3 to 18. So if we look at our set of data and we have like a -5, right, we've written down -5. We're looking at the set of data, we go, oh, we need to evaluate how we got that value. And you go, seems pretty obvious. No, because maybe it's in the experiment. Like, did somehow a different die get stuck in there? Guess I'm not sure how it turned negative there, but did you have the right dice? Did you have the right number of dice? Was it in the actual measurement? Like, did you try to read the dice in the dark? I don't know, with Braille or something, who knows? Was it in recording the data because you wrote it with a crayon or something like that? And I know that sounds trivial, but I tell you it is not. It's called error analysis for a reason. And the reason is, and here's my first major point I want to make here. It's called error analysis because performing science is fallible. We can do science wrong. We can do it badly. Science is fallible, but the hypotheses we draw as a part of science should not be. We should be able to make hypotheses based on our best data, and we should not make hypotheses unsupported by our data. When we have values, as a scientist, when we have values that challenge our hypotheses, this should make us pause. Like if you see a -5, you go, can I do that? How did I do that? It should make you pause. It should be exciting, actually. Finding something that contradicts or challenges our hypotheses is exciting. That's what science is all about. But it's called error analysis because these values may indicate mistakes on the part of the scientist, which happen, right? Every scientist is also a human first. And maybe you did something wrong. Whoops, I measured something out wrong. I didn't have the right chemicals. I didn't use the right whatever. I thought I set the voltage properly. I didn't. It happens. But here's something more important. It could also indicate bias. And Keeping On did make a point about that. Were the sources unbiased? It could be we start designing experiments because we want a particular value. We want to reinforce a hypothesis that really requires testing. But we don't want to have to admit that we need to test this hypothesis. It could also indicate experimental flaws, that when we take a set of data, the data may be perfectly valid, but we're not measuring them very well. We're not measuring values. Our method of measurement, could be the wrong technique to measure something. That could happen. But it could also indicate data mismatch, and this is pretty important. Data mismatch would imply that we are not measuring values. We're not acquiring a set of data that even supports the hypothesis we want to draw. This is a huge point. I'm going to return to this, okay? I'm actually going to return to all three of these, but later on. At the end of the day, at the end of the science class, error analysis is the central point, is the fulcrum on which the scientific method turns. Error analysis is how science self-corrects. If you can't correct your own data, if you can't correct your own process, you're screwed. You're really screwed. And it doesn't just stop there, because it's possible for scientists just to go, that is contradictory data. Just throw it out. You need to know why you throw it out. If you're dismissing contradictory data, that's indicative of poor science, period. It's coming from a scientist, okay? Told you I was a professor even, so there you go. I'm going on record with that. Dismissing contradictory data is indicative of poor science. If you dismiss contradictory data, this should make all of us pause and go, what's this hypothesis intended to achieve? If you're going to dismiss data to support a hypothesis, what are you trying to achieve with said hypothesis? So I have some fun examples now. Now we've moved past all the theoretical stuff. Let me see what else we have here. So Louise does make the point, flipping a coin is not so predictable, not necessarily 50-50. No, I mean, we are talking about complex systems, complex and complicated systems. When you're looking at a coin is not in isolation, right? You have a whole system. So flipping that, so then there's a distinction too. I should make a difference. Systems theory defines things that are complex and complicated. Complicated just means, well, it doesn't just mean. Complicated means there are a lot of variables, I don't even necessarily want to say variables. There are a lot of things, that's pretty sciencey, a lot of things that could affect the outcome of something. Complex means that the initial conditions are very important. So if you have one set of initial conditions, you will go down into a different set of results, whereas if you have a separate initial conditions, it could drive you down a different set of results. So systems theory makes this whole point. And when you look at flipping a coin, you go, well, seems pretty easy, right? There's the rotation of the Earth. There's the Earth moving around the sun. There's Jupiter out there somewhere. There's a lot of things that go into that. And yeah, it's mostly predictable, but not entirely predictable. And that's why we talk about probability. Probability was where 2 sigma comes in, and I'm going to get to that. But where we start talking about, well, is the quality of the data based on can you reproduce it at least? So, and what would be your margin of error when you try to reproduce it? So, Margie says, I imagine getting statistics from qualitative data is a whole extra level of potential error sources. It's a good question. Oh, we have Legend, by the way, who says that I'm popping up on his feed again. Hey, Legend. Good to see you. Margie also mentions that her mother founded the International Institute for Qualitative Methodology. It's pretty sweet. Qualitative data, yeah, it's a fascinating point. You can get qualitative data that that can be statistically significant, or can withstand statistical analysis. I have a great example, but I'm going to hold it to the end because it's I'm just going to hold it to the end. How about that? So qualitative data, though, just to make sure that everybody gets this, qualitative analysis means that you're typically looking at some sort of subjective measurement. A great example would be, say, whether or not gender affirming care improves your life. It's hard to measure that quantitatively. There have been attempts to do so. Johns Hopkins, back in the late 1970s, did a whole study on trying to quantify whether or not gender-affirming care made for a better life. And they studied things like whether or not somebody entered into a heterosexual relationship, whether or not they stayed out of prison, whether or not they could keep and hold a job. And they found there was no difference between people who did not receive gender-affirming care and people who did. And so then they say, well, obviously gender-affirming care is not efficacious. And so, anyway, but do those measures actually make for a better life? Those scientists said, well, this is how we're going to measure it. But qualitative, if you were to say, well, is your life better? Like if you were to ask me, has gender-affirming care improved my life? Yes, unequivocal yes. Can I quantify that? Is it like 6.2% better? Is it 60 point something? No. But sometimes, so my particular analysis is qualitative. And you can take the same qualitative data over and over again for like the course of 3 years. Now we have 900 data points, right? Now 1,000 data points over, over the course of 3 years. You can have that taken by 90,000 people. And so now you've got whatever that is, 2 million data points, So you could do some statistical analysis on this. And part of the reason why qualitative analysis has been dismissed, particularly by data people like I am, although I'm sitting here defending it, is because it's not strictly reproducible. That is, if you take 2 measurements, they may be dramatically different. If I started off, like there are days when I wake up and I go, oh, my life sucks. And if I were going to take if it was just a yes or no, is my life better? I would say no. And then sometimes yes. If, on the other hand, you turn that into like a graph of 1 to 10, 1 to 100, 1 to 5, who the hell cares? Every day we could probably see, not probably, it is possible to take those values, and even though they are qualitative, observe an overall upward trend. So it depends on how you design these experiments. So Margie, this was a great question. I'm actually going to jump into that in just one sec, but it's a great question. So, qualitative data sources it is a new level of intricacy, but it's something you can design experiments around. So here we go. Let's see. Legend says, yeah, I've been thinking about the last time, and although I still am sort of conservative on the trans issue, I'm slowly opening my mind about it. I'm going to tell you, Legend, I didn't walk away from that thinking you were a horrible person. I certainly didn't walk away from it thinking, boy, I hope I changed this person's mind. I'm glad to hear that you're back. I'd love to continue, having this conversation because it's, it's well worth having. The conversation is well worth having. And I want to thank you again, first of all, for showing up here and also for giving me that feedback. It's a really fabulous piece of feedback. Thank you. This really means a lot to me. So Brenda makes the point. So Ronald Kaus, I'm not sure how you pronounce that, but says, if you torture the data long enough, it will confess to anything. I think that's a good way of putting it, for what it's worth. Let me see. And then Keeping On says, fuzzy logic is a real subject. Using sometimes are pretty good in a logical way. Yeah. Yeah, I don't want to go into that at the moment. Let's look at some examples of statistics in the real world. I want to point out first, science comes from a complete set of data. Science creates, let me say that. Science creates a complete set of data, right? Statistics allows the set of data to be interpreted, typically. Error analysis ensures the experiments and the hypotheses match up. It's the way to keep science and scientists accountable, and for that matter, actually statisticians. So at the very beginning of this conversation, I asked the question, what is normal? And my friend made reference to 2 sigma. 2 sigma, when you're looking at distributions, so this is something in statistics, 2 sigma creates what's called a confidence interval. That is a statistical term defined as, it's an indication of confidence, confidence, indication of confidence that the next measurement you're going to make is going to fall within the interval, so the numerical interval of this range of data. So hopefully that makes it clear. So if you had, like, say 3 to 18, if you were going to say, I want to know that the next measurement I make is going to fall within 3 to 18, the confidence interval should be 100%. You've covered the entire range. If you're going to say, I want to know that it's going to be within the interval of, say, 5 to 9, that's a smaller interval. And so we can make computations around this to say, well, we have a certain amount of confidence that it will fit within this. And this is related to probability theory quite a bit. But I want to make clear, so this is an indication, right? So I think I said that. Indication that the next measurement is going to fall into that interval 95% of the time. Okay, so that's a probability there. But it is not an indication that the remaining 5% of measurements are irrelevant or may be dismissed. All right, I'm going to go back to what I said at the beginning. Science will generate a complete set of data. It's not a 95% of data. It is a complete set of data. So here's some tools. I'm going to give you some tools. Statistics in the real world tools. Oftentimes, when we look at something like a confidence interval, we need to ask the question. This is the first question. Question 1, when hearing about statistics, is to ask of what? 95% of what? What are we asking here? What is the 95% is? What is the data set? What is the full data set of which 95% represents whatever it is we're going to measure? So let's put this into the real world. It turns out the population of the United States, there are 350 million people here. So I live in the United States. 350 million people here, which is 4.4% of the global population. I mentioned that 2 sigma is a little bit more than 95%. It's like 95.3%, something like that. So if we were going to measure where people live on the globe, The United States, the entire population of the United States is outside 2 sigma. There is less than a 5% chance the next person observed will live in the United States. This is just statistics. Does this mean that the people living in the United States should be dismissed? Does it mean that the data is crap? Does it mean that, statistically speaking, the population of the United States is irrelevant? No. But let me turn the volume up just a bit, crank that up just a bit. If we take the population of the United States, and then we add in Europe, and then we add in Australia, we have just over 1 billion people, which, globally speaking, is still only about 14% of the population. 14%. Which means from that, somewhere around 9 out of 10 measurements that we make of every human on the globe is going to fail in the confidence interval. 9 out of 10 of the people that we measure will not live in the United States, Europe, or Australia. Once again, I want to say that doesn't mean the United States is statistically insignificant. It doesn't mean Europe is statistically significant. Australia may actually say to you, yeah, we're fine being statistically insignificant. What it means is that you have to ask, of what? 95% of what? But let's go in the opposite direction. Here's a fascinating point. It turns out just recently, so there was a survey, a Gallup poll that just came out recently that said that the queer community, the percentage of people in the United States living openly as queer, is just under 10%. It was like 9.3%, I seem to remember. Now, this does not include people who don't live openly as queer. And I've seen estimates that might be that range anywhere from like a real number, 17 to maybe 25%. Okay, let's take the smaller value of that, 17%. 17% globally of the population would identify as queer. Globally, that's greater than the population of United States, Europe, and Australia combined. There would be a greater chance that the next measurement you make, there is a greater chance of that person identifying as queer than living in the United States, Europe, or Australia. So there we go. We need to always ask of what. If somebody says, well, that happens 3/4 of the time, really 3/4 of what? What's the complete data set? And why are we dismissing what could actually be a very large number if you have a huge data set? So hopefully that one's good. When we hear these statistics, why is this number important? That's the question. Why is this number important? What does that value mean in comparison to the entire data set? What is the entire data set? And are we trying to dismiss data that we should not? So there we go. The next question to ask is whether the data set fits the hypothesis. So I have a pretty good example here. Science has observed, I personally have not, but science has observed, statistically speaking, humans with higher testosterone in their bloodstream, so higher blood concentration of testosterone, are statistically stronger and faster than humans who have low testosterone in their bloodstream. And this has been used as an argument to prevent transgender women from competing in women's sporting associations. The implication there being that transgender women would be assigned male at birth and necessarily have higher testosterone and would therefore be statistically stronger and faster than those weakling women who are assigned female at birth that have low testosterone in them. But the data set here is all humans. Data set's all humans. It's not the set of transgender women. It's not the testosterone blood concentration of transgender women. It's not the testosterone blood concentration of cisgender women. This data set is not a measurement of testosterone levels in any of the women necessarily. This data set is not applicable to the hypothesis. Okay? When you're going to look at people who do not actually fit, it's because it's actually taking people who would never compete in women's sporting associations, people who would never compete in it. They're trying to use that data to make a hypothesis that This is why transgender women should not compete in those women's sporting associations. This data set doesn't apply to the hypothesis. So we need to ask that question too. When somebody gives you a hypothesis, you say, is this data applicable? Does this make sense? That's question number 2. The final question here, and I'm going to go to comments, I swear. The final question to ask is whether the data even supports the hypothesis. A really, really good example came out a couple of years ago now. Yeah, a little more than a year ago. The Cass review acquired a set of data. We don't know if it's a lot or not because Hillary seems to have lost it. That's a bummer. But the Cass review, the board there, acquired a set of data. The request, the commission, was to test whether gender-affirming care was financially efficacious. When I say financially efficacious, you know, did the healthcare work? And ultimately, was NHS England getting its money worth from allowing minors to pursue gender-affirming care? Now, the data that was measured is quantitative. You can count this. Okay, it's a number. The data is whether doctors who are general practitioners would refer their patients, these minors, who went in looking for a diagnosis of gender-affirming care, whether those patients were referred to dedicated gender clinics. Now, I've never lived in the UK, so I'm not entirely positive how this separation occurs, other than you start by talking to some doctor, and then at some point you go to a dedicated gender clinic. So that's what this data is. And keeping on, just to go follow up with what you said, this does not account for the bias of those general practitioner doctors, some of whom were actually surveyed, and some of whom answered a question with, I do not believe transgender even exists. I think I'm paraphrasing that, but they said they don't even believe that transgender children exist. So this data set doesn't account for the bias of the doctors, because that was a subjective decision. It's quantitative, right? You've got a number of patients referred. But the way that they referred was subjective. There is a bias that could happen with the doctors. It also doesn't account for the satisfaction of the patients. Like, were their lives better? No answer. And that review board, Cass review board, didn't bother to ask. They don't even care. It also didn't account for any patients, and I have no idea what the number of this might be, but it doesn't account for any patients, minors, who ended up going on to private healthcare, private gender care clinics, because the wait was just too long, because it's like 7 years. So it's like, is it worthwhile, even to wait? So it doesn't take into account any of these 3 sources of skew that might occur in this set of data, some of which are pretty important, like the bias of doctors. That's a big one. This is not a measure of the quality of the healthcare. Right? And if it's not a measure of the quality of the healthcare, it's not a measure of the efficacy of the healthcare. We don't know if it worked well or not. And so ultimately, it's not even a measure of whether NHS England got its money worth. So this data set, this big, huge data set, not trumped, I guess, but put together by the Cass Review Board, does not even directly answer the question NHS England asked. Now, Hillary Cass answered answered the question, said no. But we have to ask the question of her, how did you come to that conclusion when you have a set of data that doesn't even support it? So I'm going to look at comments here. I've got a little bit more I wanted to go on that, but let's see what we got here. Let me see. Fuzzy logic, 2 standy deviations. There you go, Mischief. All right, Angela says, my opinion is that my life is better since I transitioned, but I cannot quantify it. Yeah, that's hard to do. But for what it's worth, that's medicine. For the most part, you can't quantify that. It's the same with knee surgeries. It's the same with open heart surgery. It's the same with heart surgery stents. It's the same with diabetes medication. There are a lot of things that you can go, well, yeah, my life's better. Can we quantify it? That's the way medicine works. So Angela says a person can't give an exact number for it. Right. Also, a person's lifestyle and mental state would change the results. Very true. And that's why that particular qualitative view piece of data there is considered sort of weak data. So sort of fascinating. Keeping on says, wow, I believe that popped up when I said something about the population of the United States being statistically insignificant. Miss Chief says, Americans are abnormal. That's no doubt. We definitely all know that. So let's see. Margie says she heard that 30% of Wellingtonians in the last census identified with a rainbow community. 30%. Yeah, that's pretty good. Dang. Miss Chief says, which I don't know what my number was. 400 million? I can't remember exactly what it was. That's enough for a queer nation. Definitely. I make firm-wristed gestures at the streets. Right. So Margie says she is AMAB, but take bicalutamide, so testosterone has zero effect on her. Well, you know, there's a lot of things that make testosterone, that you can have high testosterone blood concentration, but not have it do much for you, right? I mean, if you have testosterone insensitivity syndromes, there's a lot of things. And I mean, some of this comes even just from nutrition. Some of it comes from lifestyle, sedentary lifestyle versus active lifestyle. It's not the same. You know, testosterone blood concentration is not the same as sporting, capability. I'm trying to think of a word, but sure, that'll do. Okay, so Miss Chief says, yeah, you got to go to GP first, and then it's a lottery after that. Oh, gosh. Lottery biased by social class. Fabulous. Good goddess. All right, so Angela says the first GP doctor she went to said he would not refer her as a trans woman. There's a bias right there. So you are an adult, Angela, I'm assuming. You might answer that if you want to. But the CAS review specifically looked after minors, right? It wanted to see are puberty blockers in particular efficacious for minors. So you give me a piece of data that is fascinating and doesn't even talk about minors. All right, so statistics. If we're going to pull all this together, the three questions that I mentioned, if you're going to get a percentage of what? What is the complete data set? All right, what is a complete data set? Question 2, what was my question 2? Oh yeah, does the data set fit the hypothesis that ends up being drawn? And then question 3, does the data that you measure even support the hypothesis? And those are a little different, but a little different. So if any of these seem suspect, I mean, these are great questions to ask of anything. If you have a politician who says, this is why we need to do X, you need to ask about the motive of the hypothesis. What benefits, ultimately, would be gained by silencing a naysayer with a wall of numbers? Because it happens a lot. You throw out a wall of numbers, right? I mean, I even did it. I'm like, well, if you were to take US, Australia, and Europe, 5%, 1 out of 10, yada, yada, 4 billion, you can silence somebody with a wall of numbers very easily. But that wall of numbers doesn't necessarily mean anything. What benefit would somebody gain by silencing you with a wall of numbers? Then ask yourself what benefit might be gained by appearing to look scientific. If it appears like you have scientific proof of how that hypothesis is applied, that's important to ask too. What's the benefit gained by that? So in this case, we could go back to the testosterone blood concentration. What's the benefit gained by appearing to have scientific proof? If that data set doesn't fit, what's being gained here? Now there's political reasons for this, but what's that benefit? And then the biggest question, the top level question, who's affected? Ultimately, who is affected by people who get swayed by walls of numbers and by the appearance of scientific and yet unsubstantiated numbers that ultimately come down to statistics? So I'm going to return to the question that I started this section off with. What is normal? Here's your science answer. Normal is the complete set of data. It's not statistics. Normal is the complete set of data. If it's been observed and you can rule out that your measurement was done poorly through error analysis, that's valid data. And if it appeared in nature once, it almost certainly implies it will appear in nature again. If it appears in nature, it is normal. Normal is not about statistics. Normal is about nature. And anything else, any set of data, any statistics put on top of that data, any hypothesis drawn from the statistics from that set of data, and any political agenda done from that hypothesis is interpretation. And worse, it's likely to be interpreted in a way that's going to promote some sort of political agenda for a particular group of people. Statistics only shows us what is common and frequent. But I've written now for almost 3 years that common and frequent are not the same as normal. And we're never, ever, has never been the same as normal. I do have one last bit before I wrap the whole thing up here. But let's see. So Angela says she was 30 years old when a GP told her he would not refer her. And then Margie says, when the topic began today, I immediately thought of how to lie with statistics. And I think that's a lot of what it is. You know, it's really easy to use statistics and sound, I think the word I want to use is compelling. It's easy to use numbers because it has the sense of science to it. The sense of science. But as my little wrap-up bit here, for what it's worth, my little wrap-up here, I want to say, now that I've talked about science, how you get science, the scientific method, when I talked about statistics, you know, what statistics might give you, error analysis, keeping science accountable, self-correcting, all of this. Not everything that we come up against is scientific. Statistics is not science, and I will say this much. Statistics, when you're given them, statistics is not the same as science. And if you ask for substantiation, if somebody says, oh, it's 95% of the time, asking for substantiation around those statistics is science. That is what scientists do. Those are usually the foundations that you use to move forward, to make new scientific observations. So maybe you can continue to work on your theory, your hypothesis. That is science. It's questioning the statistics and seeing if you can break them in some way. Asking for substantiation. If you have somebody who tells you, here's my statistic, and you ask for substantiation, that's science. So I say go and do that. Dismissing data, just out of hand, dismissing data as statistically insignificant or statistically unimportant is going to indicate an agenda. That's it. It indicates an agenda. That does not indicate science, because science is the complete set of data. Why did we get this complete set of data? If you have a hypothesis that does not explain a complete set of data, you don't have a good hypothesis. Any failure to explain and substantiate the data or the hypothesis ends up being nothing more than a political opinion. It's not science. Because science can be explained. Politics, not always. So as I mentioned, not everything is science. And I had a good conversation. I don't know if Grief Foundation is here today or not, but Grief Foundation had a back and forth after a live stream that I did, where I ended by saying, listen, you're asking questions that we need to ask. It is important to ask questions about ethics. It's very, very important to ask how humans should live with other humans. It's very, very important. And not every opinion that we're going to come up with can even be substantiated by science. And here's my non-statistical example. The Declaration of Independence. When you read that, I think it's the second paragraph, begins with the words, "We hold these truths to be self-evident." Self-evident. Self-evident. They held truths. They held tenets as truth, but they're self-evident, which means not requiring proof. They're not going to give you proof. They don't even think they need to give you proof. You can't tell if all humans are created equal. There's no scientific test to determine if all humans are created equal. There's no scientific test or even statistical data test to determine if every human is endowed with certain unalienable rights as they wrote it. The point here is that there are truths that are purely philosophical. There are truths that are purely political. And it's absolutely important to ask these questions. But before we start using science, we have to ask if science even plays a part in that political opinion. It's okay. It's okay to hold a political opinion. It absolutely is. In fact, I would call it critical to hold political opinions, even if you can't explain why you hold them. Right? It's good for you to think about how humans could live with each other, even if you can't explain why. But it's not all right to pretend that incomplete statistics are the same as science. It's also not all right to diminish the human experience and to diminish humans because they don't fit into whatever statistics you've got. That's not all right. And so that's the end of my point there. I see Grief Foundation showed up. It is good to ask these questions. It's absolutely good. But when these questions are asked and when they're justified, rationalized, potentially substantiated by statistics, it's important to ask those three questions. What does this data mean? What do these statistics mean? And then determine, is this a political opinion or is this something that is scientific? And I'm not going to say that scientific is necessarily better than others, because I am very, 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 very emphatically going to say that I also hold these truths as self-evident, that all humans are created equal and all humans are endowed by their creator with certain unalienable rights. I believe that. I can't prove it, but it's critical that we make this distinction here. So there we go. I'm going to go through some of these comments here. So Keeping On says in math normal is perpendicular. Yeah, I know. There's also the normalization. I love also normalization, right? Where really what you do is you can scale multiple sets of data to a standard, so that you can say, you can make disparate sets of data appear at least comparable. So normalization. It's always fun. Angela says most people don't understand statistics. So true. They really don't. We look at statistics and say, well, let me finish what Angela says, because Angela goes on to say you can prove anything with statistics depending upon how you analyze the data and prepare it in the size of the sample. Yeah, it's true. I have a great example, and actually, Grief, I'm going to, this fits into what you were saying, because Grief Foundation says I'm ignoring experimental design. Thank you for calling me your love, though. Grief, I don't know if you were here earlier on. I was mentioning experimental design, and when I talked about error analysis, especially in my discussion of this error analysis book I've had for 2 decades, longer than that, like 3 decades, I did talk about experimental design and how experimental design does affect the quality of the data. And error analysis is the way we keep the scientific method self-correcting. So I'm going to get into this really shortly. But as far as proving anything with statistics, at one point I got my I won't tell you who sent it to me, but somebody sent me an article. I don't know if it was the actual article, but it was a scientific journal article, because it was published in a scientific journal. And the article says that people who eat meats are healthier than people who don't eat meat. And the person who sent it to me said, "See, this is why I'm healthier than you." At the time, I was eating vegetarian and had eaten vegetarian. In fact, I've largely been vegetarian most of my life, or a significant proportion of my life. So he sent me this to say, "See, you're wrong. You shouldn't be a vegetarian. People who eat meat are healthier." So my wife, being a scientist as well, went and looked up the article and looked at the complete set of data, because that's really what you need to look at, right? Like, who cares what conclusion these people drew, because they could have drawn it from crap data. So it turns out it was a significant set of data. I don't remember N, the sample size. I mean, I think it was on the order of, 5,000-10,000 people, quite a few. So 5 or 10,000 people. And for what it's worth, it turns out that, so keeping on's giving me some numbers there. There's a wall of data, a wall of numbers there. All right. So it turns out that this data was self-reported. That healthy had to do with, if you ate meat, did you feel that you should be healthier than somebody who ate vegetarian? And it turns out that if you slice that data slightly differently, and I don't remember the exact demographic, it might have been education, might have been income level. Typically those two are correlated in some way. But they made some other slice of the data. They took that same data in a slightly different way and came up with the exact opposite conclusion. So you had a set of data that if you sliced it one way, said meat eaters just live healthier lives, and then non-meat eaters, vegetarians, live healthier lives. Now, ultimately, this came down to health, which should be presumably somewhat of a medical opinion, but it was a self-reported thing. So somebody said, "Yeah, I just feel like I should be healthier." Totally. It so happens that people who are vegetarian tend to come from different places. I mean, it might be religious, like in Hinduism. It might be philosophical, as in Buddhism, which I guess could be religious as well. Or it could be based on science. So why are people vegetarian? I mean, you're bringing in Eastern religions or science, like education. And so you go, well, I don't know, would these people have a better sense of whether they would be healthy? If you're doing it for religious reasons, there's no doubt you would say, well, yeah, of course. Otherwise, our religion wouldn't promote it, right? So anyway, to sum up what you're saying, Angela, most people don't understand statistics. This was a set of data that was used to make opposing journal articles with two different conclusions, same set of data. And so, Grief, it's a great point. In this case, experimental design, what they measured was a person's subjective sense of their own health. And, I don't want to go into the Dunning-Kruger effect so much. Usually people with lesser education, generally people who are less skilled at whatever it is you ask somebody, have an inflated sense of how well they do it. So the other thing too is, I'm trying to remember what this effect is, but we tend to, if you want to talk about distributions, it's absolutely a bimodal distribution. When somebody says, how well do you, say, drive a car? You usually end up with two big peaks in this distribution. One is people who say, I am the greatest driver in the whole goddamn world. And that person's totally wrong. For the most part, I think something like 70% of drivers think that they're like in the top 10% of drivers, which obviously can't occur, right? So, but then you also have the people who go, ooh, I don't know. There's so much to driving. Like, do I always stay within my lane? Maybe I don't. Do I always turn on the blinker? I'm not sure. So then you have a lot of other people who think that they're really way bad. I tend to be on the, I think I'm really bad at everything kind of side. And then you have the people who think they're really good. And usually the people who are really bad are looking at them going, hey, you're awful. Maybe I'm better than I think, but not always. So anyway, experimental design does play a huge part in this, Grief. There's, if we're going to talk about qualitative data, yeah, but we can even look at it in terms of quantitative. And I don't know if you heard what I was talking about with the CAS review board and the data set that they generated. But I talked about experimental design right there, Grief. So it was an interesting, it's an interesting point. And I'm not ignoring it. That was sort of my point. I've talked now for an hour and 10 minutes about how experimental design is really the point in this, not the numbers that come out of it. So Margie says the spaceship in Wall-E was called Axiom. This was the perfect name. They held their truths to be self-evident and were wrong. Well, that's a good point. Yeah, axioms. Axioms are logical statements, or statements. That is not necessarily logical. They are statements that you can't necessarily prove. Usually you make axioms at the beginning of a debate. When you have a debate, you don't generally do statistics. Debating with statistics is useless. You want to start with an axiom that both sides can accept. And then from there, you can build logical arguments on top of them. And they're logical arguments because they're based on a fundamental that neither side goes, well, I can disagree with that. So if you can make a logical argument that's based on something that's a definition, at the very least, that's held by both sides, yeah, that's when you can have a debate. So there you go. Axioms. Axioms are philosophical, usually philosophical truths that can only be self-evident. And I don't even want to say law of gravity, right? Theory of relativity. We still think those are probably true. But I mean, there's like a level of quality of hypotheses, right? You start with a hypothesis. You got a set of data and the hypothesis seems to match it. If it seems to match most sets of data, you might advance that to a theory. And if you can come up, typically you have to have a mathematical way of representing this, but if you have a mathematical way to represent whatever the phenomenon is, that might advance to a law. We have very few laws. Law of gravity is one of them, right? There's electrochemical things, Nernst's law, there's Ohm's law, V equals IR. So there are various things that we go, well, yeah, I mean, we can model this mathematically. And because because we model it mathematically, every measurement we take actually is based on our mathematics. And that's when it turns into a law, typically. You end up with something self-defining, which is, there you go. So, all right, let me see what we got here. Mischief says, never mind snaps at Amethysta. What about Heather the Hermit? Who is that? What in the what? Let's see. All right, so keeping on, so here's some wall of data. So this is interesting, yes. So 2 standard deviation, 2 sigma, is 95%, a little more than 95%. This is 95.3%, I believe. To make this totally clear too, a standard deviation, if you have a set of data, and I swear this won't be a statistics class, but if you have a set of data, a standard deviation is an indication of how each data point differs from all of them. So it's a way of relating the quality of each data point to the data set as a whole. And there's a whole, there's a big equation that you can go to, and it's tons of fun if you're that kind of person. But the point is that you end up relating each data point. So as you get farther and farther away from what's considered the median, so this is the average of all the data points, as you get farther and farther away, you would expect the frequency to decrease. And so a confidence interval of 95% implies that you have 95% of the data within that confidence interval. And that's just because of probability. That's because of probability. So 95% is 2 sigma. 3 sigma, as Keeping On says, is 99.7%. 6 sigma is like 3.4 in a million. I don't know exactly. It is definitely very, very small. When you look at chemistry, when you're looking at reagents, you generally look for 5 nines. And 5 nines comes at about 4 sigma, if I remember correctly. 5 nines means that you have 99.999% chance of every atom that you observe, or molecule, in that reagent being the reagent you expect it to. So, it ends up being whatever that is, 0.0001% impurity. And I'm going to tell you, I mean, for the most part, most science doesn't even require that. It's kind of fascinating. You know, when you look at 90, United States pharmacopoeia type regulations, boy, I'm really doing a lot of burping today. Forgive me, folks. When you look at that, I think it's 99.7. Like the purity doesn't even have to be there. 97%. I think USP is 97%. That's 3% impurity. But it's the same with like food, right? They go, hey, so long as you have less than 3% by weight, spider legs, you're cool. Sell your chocolate, Godiva, it's cool. So standard deviations is fascinating stuff. You know, what does it really mean is the point. And I think that's maybe where I wanted to go with it. Because 97%, whatever USP is, you know, that 3%, is that, you know, is that, like, do you want to eat 3% spider legs? No. No, you go, I wanted chocolate. I don't want spider legs. Don't give me, you know, give me the chocolate. I want it to be 100% chocolate. But that's hard. The harder you try to do that kind of thing, the more difficult it gets. And you reach a point where you have, you know, I think of it as like a margin of diminishing returns. Because, I mean, like, let's talk about 2 sigma. All right, I'm going to go off on this stupid tangent here. 95% of what? Right? I mean, this was one of our questions. 95% of what? Because let's look at genetics. If we're going to do genetics. Because if we looked at the, you know, right, the Declaration of Independence, here we go. All humans are created equal. Technically, it says all men are created equal. So did they use some sort of test to determine if somebody's a man or not? Supposedly they meant humans, but how are we determining if something's a human? And is 2 sigma enough? Because, right, maybe we just look at genetics. If you look at genetics, 95% is pretty poor. 95% includes all hominins, includes, in fact, most mammals, cats. all of a sudden, now you have cats. You know, we hold these truths to be self-evident that humans and cats are created equal. Now, cats, they certainly believe that, right? You know, my cat's right now going, yes, that's right. But does that mean that we need to put them into like women's sporting associations? I don't know. I mean, it might be great, right? You have like some sprinters. You know, you have, what was her name? Florence Griffith Joyner, right? You got Flojo, you got a couple of great sprinters. And you got a cat sitting at the starting line or something, right? And they go, go! And the cat's like, oh yeah, it's hot. So, anyway, cats. Right. Anyway, statistics. Does this make any difference? There we go. All right, what do we got here? So Miss Chief says she's awful at driving. Don't know how you get away with it. I mean, that's the thing, right? We all think so, but there you go. Yeah, dewy eyes to the policeman. That's the way to do it. Keeping on says, is freedom zero sum? Wow. That's a really good question. Is freedom zero sum? If you were to look at the Declaration of Independence, that says all humans. So it implied not zero sum. But it's a great point because you go, well, if I went to, let me say the Middle East, that would be a great place for me to go right now, right? If I went to the Middle East right now and I said, hey, look, all humans are created equal, they'd be like, yeah, but not you. So we're going to cart you away. It doesn't make a difference if I hold that truth as self-evident. Because that truth is not self-evident to the people to some places in the Middle East. Freedom is freedom zero sum? Oof, what a question. With religion, Keeping On says, with religion it seems so. Your faith takes away from my faith. And it's ridiculous and sad. Yeah, I mean, you know. But this is what happens, I guess, when you do not have something that can be proved. Right? I mean, so I used self-evident truths of the Declaration of Independence, political philosophy here, not religion. But at the end of the day, it's the same thing. I mean, like, I believe that's true, that political philosophy is true, but other people don't. You know, so yeah, in that case, their faith was going to take away from my political philosophy. So Margie says, in her view, love is the opposite of zero sum. That's great. The more spendthrift one is with expressing it, the more one has to give. The more spendthrift one is with expressing it, the more one has to give. Oh, I see. So if you hand out love as much as you can, the more love you can hand out. It's very good. Keeping on says, oh, give me an ohm on the range. Thank you for riffing on Ohm's law. I would just say resistance is not futile. Resistance is actually voltage over current. So there you go. All right. So let's see. Miss Chief says, I'm blazing tonight. Sounds good. Brenda says, I have an odd sense of what is fun. I absolutely do. And then Miss Chief says, she likes science. It's groovy. I talked about a whole lot of things here, and I wanted to knock out like an hour and a half. I feel like, I feel like we spend a ton of time debating about things that are not actually even scientific. We spend a lot of time trying to prove that our opinions should be valid. And I guess at the end of it, like I'm confident enough in what I believe that I can say there are some things I don't need justification for. And I guess when you get to some point, when you find somebody who says, I'm going to give you a political opinion, and I believe that because of XYZ statistics, I think that should be the first danger sign. One of the things that I was mentioning to somebody, I don't know if this was on a podcast recently, I kind of think it was. I think I gave an interview last Monday where I mentioned this. When I was going to transition gender, so I actually mentioned early on in all of the content that I've made, I initially went into the field of genetics because I thought I was going to be able to fix myself with genetics. People treated me differently than I knew I was, and I figured I could fix myself. And fix myself ended up meaning that I'm transgender and pansexual. That's what fix myself meant. And I decided sooner or later I didn't have to fix myself, and that's why I went away from genetics. But aside from that, when I started to transition, I came up against people who said, well, gender is a social construct, gender is genetics. And what I did was, rather than hold an opinion, rather than say, well, I need to justify myself, so I'm going to hold an opinion, what I did was say, I don't know enough about myself. Let me go find out. And so I went and I checked out textbooks about human development, and I brushed up on my genetics, and I, plenty of stuff. I looked at a whole lot of sciencey stuff. And I think what distinguishes me, anyway, from other people is that I ended up holding not political opinions. I ended up with a corpus of scientific knowledge, none of which justifies who I am. I think that's a big distinction. I am who I am, and that's all that there is. I just ended up so Popeye right there, didn't I? Anyway, I know that I am, and I think I could leave it at that. I know that I am, and so I ended up doing a bunch of research, and still came up to the point of I am what I am, and that's all that I am, and I eats me spinach, and I think that's okay. I think that's okay. It ended up driving different theories. My theories of identity and gender. It ended up driving those, but I started from this idea that I am who I am, and then just went and got a lot of scientific type stuff and said, well, none of that really justifies or is really what it left me with. Well, there's as many questions as there are answers, and I don't think that's bad. But I do believe that my take on all of this has been first to believe that we are who we are. We don't have to justify that necessarily. We just are who we are. And so attempting to justify anything is probably the first indication that something bad's going on. Something bad's going on. So let me see what we have here. I got a Cookie Monster, it looks like. That's not bad. So Margie says when potential is applied across resistance, power is yielded. Yes-ish. I mean, it's current. You know, if you apply a potential across a resistance, a current. But power is coulombs per second. You know, current is measured in sorry, it's not coulombs per second. Yeah, it is coulombs per second, I believe. And current is measured in coulombs. So current and power are very, very closely related. You know, power is voltage times the current. So you have the idea of how strongly you're pushing these guys and how many of them you're pushing. And so there you end up with watts, right? So you're going to have joules per second. So you go coulombs per second and then volts, and a volt coulomb is a watt. So a watt per second ends up being joule per second. Screwed that up. I'm not looking at any books here. What? All right. If I disagree with, Keeping On says, if you disagree with the concept of gender, refer them to these 30 major medical, pediatric, and psychiatric organizations. I mean, it's a great point. At the end of the day, what I'd like people to do is instead of trying to agree or disagree, instead of saying, well, prove to me gender exists, is like just kind of look inside. I mean, what in the what? Why are some of these things we try to put together just because we want to justify our own prejudice? And it's okay if you hold these prejudices. I'm not even going to tell you to change them. I am going to tell you that your prejudices need to be recognized as such. And I think we just leave it at that. So, all right, I am going to let this go now. It just struck me. I intended to do my my station identification every 10 minutes. I'm not here in Morse code doing do to make me throw down my call sign. But I am Amethysta Herrick. And you've been watching a live stream called Identify Yourself. Today I talked about everything that's good and bad about science and statistics, and at the end of it all, Margie calls me beautiful and purple, and they love the heck out of me. So, what do we got here? Miss Chief says 1 amp is 10 to the power of 18 per second, or something like that in electrons. Yeah, Coulomb's some weird. A Coulomb is something weird. Coulomb was a weird guy, though, for what it's worth. All of our... I was going to shut it down. All of our electrochemistry is weird, because it's not like... Because we defined certain values, and then when this is awesome, we've got these certain values, and they're totally easy, right? 1 volt. This is super easy. And then we went, oh, that doesn't really work with, the natural world. And so we ended up with things like, 3.4 times 10, 3.4169, electrons per whatever. And you go, wait, what's 3.41? Why isn't it like 6? Like, shouldn't it have been like 1,000 or something? We were the ones who were able to define this, but we defined certain things, and then we started doing experiments and went, oh, crap. Maybe we shouldn't have defined it like that. So anyway, it is funny. Anyway, Margie says that, I'm not saying you're wrong, Margie. Margie says voltage equal to potential, yes. So a voltage across a resistance, she's saying, yeah, voltage across a physical distance yields a current, maybe, because if the resistance is absolute vacuum, maybe not. That current across the same resistance yields power. Yes, but it is not necessarily, it's not the same value. The power is not the same as the resistance, I guess is where I was trying to go. So, all right, that's the whole thing. I have been Amethysta Herrick. I'm going to be, when I shut this down as well, but talking about science and statistics and all the good jamming stuff. So thank you very much to Keeping On, to Miss Chief, to Grief Foundation, to Louise, and Margie, and to as many other people that I didn't mention. Lizzie, thank you so much for moderating. Legend, thank you for showing up again. It's pretty sweet. I got to see Brenda. I'm curious where Genevieve is. I wish I haven't heard from her yet because I think she had some surgery this past week. So anyway, that's going to be it. Miss Chief sends me 10,000 Tesla biscuits, so long as it's not 10,000 Tesla Model Ys. That'll be it. All right, thank you everybody. Talk soon. Bye.